No, I can hear you. So we can register.
Okay, good morning once more.
Good morning, sir.
Good morning.
Okay, thank you very dangerous for that. And I think we can start off. The lesson goes up to around 1:30.
Yes.
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 Perfect. So, of course, you're going to be with me, Mr. MBALUKA. So, very, very interesting and fascinating chemistry lesson about the revision is all about, because this is a revision session, we are dealing with industrial chemistry. And maybe somebody can just remind us, what is industrial chemistry? What is industrial chemistry? When you talk about industrial chemistry, what are you talking about? Anybody who can raise up your hand, and of course, Jeff Mutungi, can you give us the meaning for that?
In my understanding, industrial chemistry deals with commercial production of chemicals and related products.
Yes, so industrial chemistry is really the production of chemicals. No, anything that is normally occurs and is a large scale manufacture of something. But just let me to clarify that. The topics that in chemistry we are going to deal with industrial chemistry, you can say those are simply the chemistry of metals and nonmetals. That's whereby you're going to find most of the industries will be making compounds or other products that are related to either metals or that's very much important. So the entire industrial chemistry focuses on the study of metals and nonmetals. So let's look at some of the issues, or rather some of the areas that are likely going to, because these are revision, I'll be able to show you, like now, which questions are we likely going to see? Which questions are we going to find related to the chemistry of metal and metals? Of course, I'm not going to tackle metals because, first of all, metals you have not covered, but you have covered carbon, you have covered nitrogen, you have covered chlorine, you have covered sulfur. So that's the concept that I'd like to talk about. The chemistry of carbon, the chemistry of nitrogen, the chemistry of sulfur, the chemistry of chlorine. Are we together?
Yes.
Yeah.
Very good. Now, in that kind of a scenario, I like to, of course, I've also seen by Gikonyo, and of course, remember this thing is also live, is being streamed. In that kind of a scenario, we go to the next. And the next, now we look at now, first of all, one of the areas that the examiner will ask you will be on preparation of gases. I want to believe, whether you're able to see my screen, it's clear?
Yes.
Yes.
So now, in that kind of a scenario, first of all, we have the preparation of gases. That is an area that will encompass, will be tested much. And of course, you're not going to find any exam without preparation of gases, including the one that we were able to, the one that you did the other day. So now, first of all, you have to say, we always say that whatever you're waiting for an exam, you focus on 3 main areas. And that is what is tested, how it is tested, and what are the expectations of the examiner. That is what you need to understand. And how do you answer those kind of questions? First of all, let's focus on what will be tested. First of all, there are 18 gases in chemistry that will be tested. And you can be able to see them. We have the Form 1, we only have oxygen and hydrogen. Form 2, carbon 2 oxide, carbon 4 oxide. Form 3, we have chlorine, HCl, nitrogen, nitrogen monoxide, are nitrogen 2 oxide, nitrogen 4 oxide. We have ammonia, sulfur oxide, sulfur 6 oxide, hydrogen sulfide, and then we have the now we have these gases here. Sorry, I want to use a different color. We have these gases here, the likes of the one for organic. So the one for organic, remember, you have not covered organic. But looking at that list that I've given, those are the guys that you're going to find in the KCSE. And even in any exam that you're going to do. Apart from the methane, ethane, and ethine, the last gases that I have analyzed and organic. All the other gases, except also the one for Form 1, are under chemistry of metals and nonmetals. So they are summarized. They are normally, all these gases are going to be tested, and they fall under the topics of carbon, nitrogen, sulfur, and chlorine. That is true, isn't it?
Yes.
Yes.
Yeah, you can be able to do that. So I'm going to use the special technique, the Octopus technique. Both the chairman of the Octopus and the one who coined the word the Octopus technique, which is simply the concept of mapping technique, the mind mapping technique. So using the spirit of the Octopus and other the technique of the Octopus, I'm going to show you how you can summarize the 18 gases just using one diagram.
True.
So
Yes.
get ready for us to be able to unmask, to be able to unpack, illuminate, and demystify chemistry in a very special, pragmatic, and paragonic manner. So there's somebody who wants to record. I think I'm going to give you the power record. So we are going to do it in a very special way, and we'll be able to see. First of all, I'll also tell you how you are supposed to answer questions. We have the method of collection. Method of collection, you can be given the gas, you are told to identify, complete the gas, complete the diagram to show you can collect the dry gas, identify the mistake, justify the method of collection. And I want to give this, like there's a question that we had given you. And
Yes.
we told you to identify the mistake. You remember that question, the exam that you did?
Yes.
Yes.
Whereby it told you to identify the mistake in that diagram. Most of you rusted in wholesale because you gave wrong answers. That question was preparation of was for preparation of hydrogen. And when you're preparing that preparation was it preparation of ammonia? Then you're told to identify the mistake. Many students were telling us the flask is not slanting. Remember, we talk about slanting downwards. But remember, the mistake was the flask was slanting upwards. The flask was, I don't know whether you people, you remember that question, you still have it. The flask was drawn slanting upward. That was a mistake. Then you are told to give a reason. Then you tell us the water font will flow back and break the flask. But now some students were telling us the flask should be slanting downward, or rather the flask should be slanting. Remember that, first of all, there's nothing called slanting. Because like that gun, if I give you, if this was a flask, assume this was a flask, and I order it like that, it is slanting, although it is slanting upwards. So if you slant it in the opposite direction, like this one, now this one is slanting downwards. So you don't have to tell us that the flask is not slanting downwards. You are told to identify the mistake. The mistake is the flask was slanting upwards. The water formed will condense and flow back, breaking the flask. The other mistake was the wrong method of gas collection. Rather, collecting the gas by downward delivery was wrong because ammonia is less dense than air. So that is how you identify the mistake. There's another one whereby you are told to give the correction. If it was now giving the correction, you could have said the flask is slanting upwards, that is a mistake, it should be slanting downwards. So remember, the examiner can tell you, identify the mistake. You identify the mistake. You can be told, give the possible correction. Now you give us the correction. The other one, like that one we had given you in the case in the exam that you did was now give a reason, which should have been very clear. So gases that are collected, we have our water. We'll be able to have a look at that. Reagents, condition, and drying agent. Those are things that you're going to be given. Because you can be given a gas, then automatically they give a wrong drying agent. We are coming to that. The condition, that's the preparation of that particular gas require it or not. Then we have the equation for reaction. You need to write the equation for that particular reaction that is taking place. The setup drawn but incomplete, you are told to complete the setup. Of course, many students will talk about landing position. These are mistakes. We don't say landing position. You tell us now the flag should be slanting downward. The setup with the mistakes, case of chlorine, of course, the interchange, of course, when you can be given the setup of preparation of chlorine, but then now the examiner will interchange the water. You find that when you're preparing chlorine, you first of all pass it through water. Then you pass it through conc sulfuric acid to dry it. Then you call it by downward delivery. So somebody can put conc sulfuric acid first, then followed by water. That would be a mistake whereby many students may not be able to do. Describe a chemical test. And of course, their chemical properties. Then you talk about the uses of the gas. So let's now, let me now go to the octopus himself. So this is now the octopus technique. This single diagram is navigating and summarizing the preparation of all the gases that are in the syllabus. I want you to take a screenshot as we navigate, as we try to navigate together on how to get this. Are we together?
Yes.
But it is very good and very, very magnetic. One, about 14 gases can be prepared using this simple setup. So you don't have to get your book and draw 18 diagrams. You just need to use your wisdom. Just need to use your wisdom. That is one now. Watu waache kushinda wakinisumbua na they want to record because automatically the lesson is already recorded and will be posted in the YouTube for Alliance High School. So you can still be able to get it from there. It's no big deal. So don't start wasting a lot of time. You want to record, you don't want to record, the thing is already recorded, and of course you can be able to access it. So whatever I'm saying that this is the octopus methodology that is used to prepare the gases. I'm saying we can have many gases can be prepared using this method. First of all, you use liquid reagent is here. Then we have the solid reagent, which is found in the conical flask. So the flask will have the solid reagent, the liquid reagent will be on the distro or dressing. Are we together?
Yes.
You can simply go and list the gases. If it is hydrogen, the hydrogen, you may indicate the liquid is for hydrogen dilute HCl. For solid is zinc metal. We go for oxygen. If here we go to have hydrogen peroxide, the solid will be manganese oxide. If here we have water, here we go to have what? Sodium peroxide. Then you can continue and do summarize those kind of things like that. So wherever you write something like that, you don't have to continue writing so many diagrams. It is very easy. From there, once now the setup for the distro funnel and the flask is complete, now we go to the next step. Gases that are going to be prepared, they can be soluble or they can be needed that is simply wet or when they are dry, rather if they are soluble. We are looking at the solubility now. We have the ones that are very soluble and the ones that are slightly soluble. So for the very soluble gases, and you require to dissolve them in water or rather to prepare a solution of that, you now or rather prepare them by directing into a beaker using an inverted funnel. Are we together?
Yes.
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 Gases are
Yes.
very soluble in water. We have sulfur oxide, we have ammonia, we have hydrogen chloride gas, and we have nitrogen oxide. These gases are very soluble in water, and their solution can be prepared using an inverted funnel. But a catch is there. An examiner will come here and label this apparatus and label it as apparatus P. Then the examiner will ask you, what is the name of apparatus P? What's the name of apparatus P?
Funnel.
Inverted
Funnel.
That is a funnel. When you're told to name the apparatus, don't start telling us this one is there is no apparatus that you learned in school that is called an inverted funnel. So the apparatus is simply called a what?
A funnel.
Yeah, that is a common mistake whereby you're going to find many students will be got by the examiner. Just like, for example, when they give you that preparation of ammonia, na tumekulebolea ile round bottom flask, are you going, if you tell you to identify the apparatus, are you going to say this is a slanting upward flask? It is simply a round bottom flask. So that don't give us the orientation. Simply tell us this is a funnel. So if for the four gases, you prepare them using an inverted. And don't always think about preparation. You know, somebody will prepare a setup for preparation of sulfur oxide. Then you're told that a student from Alliance High School prepared sulfur oxide is shown. Then they are going to put sulfuric acid here. They are going to put copper here. Then they'll tell you the gas, once it was prepared, it was now dissolved in, or rather it was dissolved in acidified potassium manganese 7. Then the first thing the examiner will tell you, show how the gas was dissolved in potassium manganese 7. So again, you'll still draw. As long as the solution doesn't have to be water, you're still going to use an inverted funnel to show how you can direct the gas into potassium manganese 7. Remember that one now, the examiner might ask you, what are the observations that the acidified potassium manganese 7 changes from purple to colorless? Are we together? You can also prepare chlorine, then you direct it into iron 2 sulfate. What will be the observation? It will change from green to what? To yellow. Are we together?
Yes.
Very good. Then we go to gases that are slightly soluble in water. The gases that are slightly soluble in water, they are collected over water. Those gases over water, kuna over warm water and over cold water. So now, in that kind of a scenario, for cold water, we have the gases that are completely slightly soluble in water. We have oxygen, hydrogen. They are given all those ones are there. Then we have warm water. Warm water is only used to collect either hydrogen sulfide or nitrogen 1 oxide. And remember, somebody will prepare this gas like nitrogen oxide and then collect it over cold water. Then you're told now, identify the mistake. Then collecting it over cold water is wrong because it is fairly soluble in cold water, but insoluble in warm water. So you see now, using just this simple diagram, we have already shown you how to collect how many gases. Those are about 11 gases. Ratio of content over water. But remember that all the gases except hydrogen is insoluble in water. But all the other gases that are collected over warm water or rather over cold water, they are simply, we say they are slightly soluble in water. Any question? That one clear?
Yes.
Yes.
Very
Yes.
good. Very good.
Yes.
Very
Yes.
now, we now go to drying agent. The drying agent that can be used here is either calcium oxide, anhydrous calcium chloride, and concentrated sulfuric acid. Remember? Okay, somebody.
Anyway, tumesoma mashafu yote kabla kwenda sema kwa new beginning.
I want to mute these guys. Mute all. So do you have somebody who is very normal? Can you raise up your hand so that you can help me you can help me mute those guys? Somebody who is very normal, I can give you a call. I can make you a call to you. You help me in unmuting people. We have John Paul Obasa. Okay, good. Sorry. So, John Paul, I've given you superior powers to King Malin in Nani. Okay, I think John Paul, you'll do that because you can mute guys who are there. I think I'm not muted anyway, so you're able to hear me now.
Yes.
So we are still here and we are still analyzing this. So if a gas is now needed dry, you need a drying agent. And for the gas that are dry, we have the drying agent. You want to pass the gas through a drying agent. And all of them except the concept of carbon dioxide, whereby carbon dioxide and chlorine are very unique. Before using a drying agent, you pass it through water first to remove traces of HCl. And I don't know whether you have ever asked yourself, why is it that we want dry chlorine? And we also say chlorine is a little bit soluble in water, but we pass it over water before drying it. Why do we do so? Why?
Please pardon.
I've said during preparation of chlorine, we pass it through water. And chlorine is also slightly soluble in water. Why are we able to pass chlorine over water, then we pass it over sulfuric acid, then collect it? Why is it that the chlorine gas is not dissolving in water? Jordan Onsarigo, mute yourself and answer the question.
So I think the reason that is possible is because the hydrochloric acid is more affinity in dissolving in water, and therefore it dissolves more than chlorine. That's why it does not dissolve the chlorine.
Anybody else with another question? Another answer? That's good. That's a very good answer. But of course, I want to say, anybody else, just unmute yourself and talk. Somebody.
Okay, chlorine is soluble in water, but the rate at which it is dissolving the rate at which it is being produced is faster than the rate at which it is being absorbed by the water.
Okay, good job. But just listen to this. For both manufacture of HCl and carbon dioxide, for both manufacture of carbon dioxide and chlorine, we are using HCl, and the role of water is to absorb the traces of HCl. So what happens that when the hydrogen chloride gas dissolves in water, it forms hydrochloric acid. And chlorine and carbon dioxide do not dissolve in hydrochloric acid. So the solution changes from water to hydrochloric acid on dissolving the HCl gas. So chlorine does not dissolve in hydrochloric acid. That is why now no longer does not continue to. Are we together?
Yes.
Just be guided like that. That's the correct scenario. Unless somebody has a question. So now we go to the method of collection of the gas. The gas can be collected by upward delivery. The gas that are collected by upward delivery are only hydrogen and ammonia. Those are the ones that are comfortably collected by upward delivery. Then we have, sorry. Then we have the ones that are collected by downward delivery. Those are gases that are denser than air. Those are the gases that are denser than air. So those are the gases that are there. But now I want to give you as a pragmatic scientist, you know, tunasemanga, science is more empirical. Science is more empirical and practical than theoretical. So in that kind of a scenario, I want to prove how to use a simple method. There's a real science. You know, you're not just any student. You're a student from Alliance School, the ocean, whereby the paragon of excellence, whereby it is the true definition of being the best. So science is not about cramming, to start cramming nitrogen oxide. Like now, the other time I gave you the exam that you did, we set the preparation of nitrogen 1 oxide, nitrogen 1 oxide, and nitrogen 1 oxide. And many students could not know whether it's collected by upward or downward. So I want to give you a trick that you can use to get the density of, or rather to get the mass of air. Are we together?
Yes.
Good.
Yes.
So get ready to be magnetized. You just need to know the composition of air. What is the percentage of nitrogen in here?
78. 78%.
28.
78.
It's around 78, isn't it?
Yes.
So Andika 78 over 100 times the mass of nitrogen gas, which is 28. So to answer here, so you get 78. That's the percentage of we want to get the mass of air. Very easy. Mass of air. First of all, you get the percentage of nitrogen is 78 over 100 times the mass of nitrogen, which is 28. Give me the answer if you have a calculator there. What the percentage of what's the percentage?
21.84.
It is what?
21.84.
21.84.
Very good.
74.84.
Then the other one is the component of air is oxygen, which is around what? 20.9 over 100 times the mass of oxygen is what? 32. What are you getting?
6.688.
6.688, isn't it? The other component of air is noble gases, which is mainly argon, and is around 1%. 0.9. 0.9 over 100 times the mass of argon, which is 40. What are you getting? This kind of wisdom, you're not going to get it from anywhere. It can only be got here. Yes? Is what?
Other.
The mass of argon. The percentage composition of noble gases is 0.9. And normally this argon alone is 0.9. Then you get 0.9% over that 0.9 over 100 times the mass of argon, which is 40. What are you getting in the answer?
0.36.
0.36. Then we have the other one, the other component of air is a carbon dioxide, which is 0.0. Is it 0.03 or 0.003?
0.03.
0.03 divided by 100 times the mass of carbon, which is carbon 4, which is 44. Are you getting?
0.0132.
0.0132. Add now all those masses now. Add the one for nitrogen, 21.84. Or you add for oxygen, 6.688. You add the one for argon, 0.36, and the one for carbon 4, which is 0.0132. Those are the main components of air. Give me the mass.
28.9012.
28.9, isn't it? So which is roughly around 29. That's the mass of air. You can say The mass of air is around 29. So any gas whose mass is above 29, it is denser than air. Any gas whose mass is below 29 is less dense than air. That's how you get to a thing. It becomes very easy. You don't have to start cramming here. Chlorine is, if you want chlorine, what the mass of chlorine? Chlorine is 35.5, but we have chlorine gas, which will be what? What's the mass of
71.
chlorine gas? 71.
71.
So, denser than air. Let's get something like the one that we gave you, nitrogen 1 oxide. Nitrogen is 14. 14 times 2, that is 28 plus 16. What was that? What are you getting?
But
We want to get the mass of this gas here, so that we can know whether it is denser or less dense. This one now, nitrogen 1 oxide. Given that nitrogen is 14, oxygen is 16. So what's the mass of that?
44.
44.
44.
The one for hydrogen sulfide. Sulfur is 32, hydrogen is 1. So huh?
34.
34. So is it less dense or denser than air?
Denser.
Leo,
Denser.
let's get your point, eh?
Yes.
That's it. That is chemistry now, understand. You don't have to start cramming things. Bishangaa sasa hii tulikosea wapi? How do you know which one is denser or which one? No. Very easy. You don't have to cram those things. You just understand. The mass of air is what? 29. And you can prove in a pragmatic manner. You can use in a pragmatic manner. Anything else is dogmatism. So using the pragmatic approach, you can easily confirm the mass of air. So any gas whose mass is above 29 is denser than air. Anything that is below 29 is less than air. Nilisema John Paul, can you do the next one? Kuna mtu ameuliza swali. Uliza, inua mkono, just ask the question. Wayne is under.
Yes, Chair. And I was asking, can we say that all acidic gases are denser than air, and the ones which are not acidic are less dense?
No, that is the misnomer. That's the wrong statement. Because you see now, when you say the gas that are not acidic, hydrogen is not acidic. Yes, it is less than air. Ammonia is not acidic. It is denser than air. But you see now, we have the gas that are neutral, the likes of water. The water, no, that's an oxide anyway. We have the one for nitrogen oxide. But now, that's a very funny statement, because you see now, that statement is not confined to only the oxide that you know. We have, as you are going to advance in chemistry, you're going to find even acidic oxide like arsenic oxide. So it may apply selectively here, but may not be true that any gas that is not acidic is not any gas that is not acidic. You're saying what? Any gas that is not acidic is less than air.
Yes.
What about butane, which is C4, H12, H10? What amount of that? That's still a gas.
I was saying all acidic gases are denser. Only acidic. like I'm trying to say, like acidic gases, like okay, yes, there are other gases which are denser than air, but they're not acidic, like the ones that you've said, like ammonia. So, but just to like lesson on like trying to know so many gases if they're denser or not dense, can we just give a short statement by saying acidic gases, we know that they are denser than air, and also some other few examples there. Like I'm just trying to make it simpler, something like that.
So now, so you're meaning for gas that are acidic, they are denser than air. What if they're not acidic?
If they're not acidic, okay. yeah, if they're not acidic, they're okay. So there'll be some which are denser than air, but
So now you see
others
now
are
that
not.
statement. Now that I'm saying that statement will be wrong, because if you're going to see those that I don't want to go to those many issues that are there, because you are going to find so many of them that can also be leaked. You're going to find so many of those gases. It's true, some of the gas that are here that are acidic, like the likes of HCl, like the likes of carbon dioxide, but that's not chemistry, that's not pragmatism, because you're also going to find other gases that may be acidic, but they are not less, but they are not denser than air. And you cannot, when you say acidic gases are denser than air, you're also going to find others that are denser than air, but they are not acidic. So that one now statement does not generalize. The most important thing is just know that the mass of air is 29. And you can easily know, because all these gases, by the time you finish with the mole, you'll have mastered the atomic numbers of each. Although, for purposes of clarity, the only gas that are really less dense than air is ammonia and hydrogen. We still have others like nitrogen, which is 28, like carbon dioxide. Carbon dioxide is also here. But now, those gases whose mass range between 27 to around 32, simply 28 to 32. Any gas whose mass is between 28 to 32, its density is almost the same as that air, because you see, like if the mass of air is 29, something whose mass is 28, its density is very close to that of air, because remember, density and mass are the same. So in that kind of a scenario, these gases will be very difficult to be collected by upward or downward delivery. It's just like, for example, you find a scenario whereby you are carrying your brother who is 58 kilograms and you are 57. You tangangana sana kumbeba because mnatoshana ni kama mnatoshana to weight. Are you get the point? So in that kind of a scenario, the concept of displacement of air by maybe something like oxygen or nitrogen or carbon dioxide, whose mass is very close to that of air, will be very difficult. So those gases, if they are needed dry, they are collected using a sewage. Are we together?
Yes, yes.
Yes, yes.
Somebody, yeah? I'm saying there are those gases whose mass is between 28 to 32. So those gases, they have almost the same density as air, and therefore will be very difficult for them to be displaced downward or upwards. And therefore, the best method to collect them if they are needed dry is the use of a sewage. Are we together?
Yes.
Yes.
So somebody can even ask you a question. Explain why it is difficult to collect nitrogen dioxide, or rather carbon dioxide, by upward or downward delivery. But then you say, because it has almost the same density as air. Then we go to the drying agent. Remember, when you are drying agents, if it's a calcium oxide and anhydrous calcium chloride should be placed in a U-tube, but conc sulfuric acid should be placed in a conical flask. So somebody can draw a diagram, then you are given a liquid in a conical flask. Then they tell you, identify a suitable drying agent that can be used as drying agent Q. So some students will say calcium oxide. Remember, if you see a U-tube, it's either going to be calcium oxide or anhydrous calcium chloride. If you see a conical flask, it is going to be it's just going to be conc sulfuric acid. Are we together?
Yes.
Yes.
Yes. Yes.
Now we go to summary.
Yes.
We have 18 gases. We don't need to cram the drying agent for the 18 gases. Very simple. Just come here. Sasa huyo mtu nilimwambia kazi yake ni kumute watu wameenda wapi. Okay. Now, remember, conc sulfuric acid can dry all gases except ammonia, hydrogen sulfide, and alkenes. Uongeze hapo, that one is not captured there. Conc sulfuric can dry all gases except ammonia, hydrogen sulfide, and alkenes. And alkenes. Are you there?
Yes.
Carton.
I'm saying, are you seeing my screen? Conc sulfuric acid can dry all gases except ammonia and sulfide and alkene. I think I'll just, there's some guys here, just. So conc sulfuric acid can dry all gases except ammonia, hydrogen sulfide, and alkene. So you don't have to cram. Umeampewa tu complete the diagram below to show how you can prepare and dry sample of nitrogen, one of them, like the one we gave you. Pitisha took a conc sulfuric acid. As long as it's not ammonia and hydrogen sulfide, it can dry all the other gases, except ammonia, hydrogen sulfide, and alkenes. The other one is fused calcium anhydrous calcium chloride can dry all gases except ammonia. So all the other gases, the Q 18, the Q 17, you can dry them using anhydrous calcium chloride. Does it make your work easy?
Yes.
Yes.
Now,
Yes. Does that mean calcium oxide can dry all the gases?
calcium oxide, achana nayo, ongopa hiyo kitu. Calcium oxide cannot dry acidic gases and ammonia. Just write somewhere. Calcium oxide cannot dry acidic gases and ammonia because it reacts with them. Remember, drying agent should not react with the gas it is drying. So calcium oxide is a very dangerous drying agent. Any gas that is acidic will react with calcium oxide because calcium oxide is a base. If somebody will give you preparation of chlorine, then a petition for drying agent come a calcium oxide, then it tells you, identify the mistake, use of a wrong drying agent. Calcium oxide being basic will react with the acidic chloride gas, or rather will react with the acidic sulfur oxide, acidic nitrogen oxide, etc., etc., etc. Now, is that clear now?
Yes.
Perfect.
Yes.
Now we have the special category of gases. The special category is the one like glass retort that is used to prepare nitric fiber acid. It does not conform to any normal setup of preparation of gases. So the glass retort, preparation of nitric fiber acid uses glass retort, which is a very unique method of collecting gases. Of course, remember, this question is very common whenever you're going to be asked which gases, or rather, why we use glass apparatus in the manufacture of nitric. Nitric fiber acid, we treat it as a gas. Because when you're reacting, when you're preparing nitric fiber acid, use concentrated sulfuric acid and potassium nitrate. When the reaction occurs, the nitric fiber acid distills off because it's highly volatile. So it is collected as a gas. That's why we are putting it, or rather considering it, or rather treating it as a gas, because during preparation of nitric fiber acid, when you mix the concentrated sulfuric acid with potassium nitrate, the nitric fiber acid is highly volatile and distills off and collected separately. Are you get the point now?
Yes.
Yes.
But true, we also have category 3. The other category of gases are the sulfur 6 oxide or uses or gas reagents. Hii utakuja utaiongezea hapa chini. It uses all gas reagents. Do you have any other gas that we prepare in the laboratory whereby all the reagents are gases? Do you remember one? Except sulfur 6. What are the reagents done when you're preparing sulfur 6 oxide? What are the reagents? Yes, Mutungi.
Sulfur oxide and oxygen.
Sulfur oxide and
Gas.
oxygen. That's it. So both of them are gases. Now we go to the common reagent, the gas that I prepared using common reagent. We have the gas that require water. There are only 2 gas that require water. That is oxygen gas and ethyl. You have not tracked this one. We are coming to that later. We have the one that uses sulfuric acid. And the sulfuric acid, which gas uses sulfuric acid? We have the one that uses concentrated sulfuric acid. The one that uses concentrated sulfuric acid are carbon 2, ethene, sulfur 4 oxide, and hydrogen chloride gas. Then we have the one that use dilute sulfuric acid. We have the case of hydrogen gas. This is now the octopus technique, meaning your work is very easy. The gas that use hydrochloric acid, the gas that use hydrochloric acid, it can be dilute or concentrated. For concentrated hydrochloric acid, it is only chlorine. For dilute, is hydrogen, carbon 4 oxide, sulfur 4 oxide, even what? Even sulfur 4 oxide. Even sulfur 4 oxide can be collected using, can be prepared. Because sulfur 4 oxide, we also collect sulfur 4 oxide, prepare sulfur 4 oxide by using dilute HCl and sodium sulfide. Correct? Correct?
Yes.
Yes.
Then we have solid reagents. We have the likes of methane, we have nitrogen, we have ammonia. We have ammonia. Then we have nitric 5 acid. Nitric 5 acid, with the one that I collected using nitric 5 acid, we have the concentrated, 50% concentrated, that is nitrogen 2 oxide, and very concentrated nitric 5 acid, we have nitrogen 4 oxide. Or rather, this one you can call it dilute. Many books will still call it dilute. When 50% is still dilute. Are we together?
Yes.
Yes.
Now, listen. But this one will apply more in case you see. Ile wakati utaambiwa collect gas, now you cannot remember whether it's upward or downward delivery. Just use the what?
A syringe.
You can use a syringe. But this one, mimi nitakupenalize. I expect you, of course, initially we used to. Sometimes the exam, we are very generous with marks and we may give you that, but that is not an internal exam. But ukifika mahali ukuwa umekwama kabisa, tumia tu syringe. We may not give you marks no more, but I've already told you how to know whether a gas is denser or less dense than air. Tumesema mass yake ni ngapi?
29.
Mass of air is what?
29.
29. If that is denser, that has a higher mass than 29, it is denser. Less than 29, less dense. Period. That's it. So we can now continue from there. Tuko sawa hapo, eh?
Yes.
So you can now go and summarize on preparation of gases. Also look at now like the test. We are, nobody will tell you to state the test for oxygen. We'll tell you to describe. So when you're going to describe, and normally for test, write the following. The tests of the gas that are likely going to be tested, whereby you're going to be describing a test for gases are as follows. Andika, oxygen, hydrogen, carbon 4 oxide. We have something like ammonia. We have chlorine gas. We have hydrogen chloride. We have hydrogen sulfide. We have sulfur 4 oxide. Those ones are darling of the examiner. Rarely will you find somebody telling you to describe test for carbon 2. What is the test for carbon 2? Does it even have a test? Huh? We may also have special interest of nitrogen 1 oxide because it is the other pleasant smell. So, are we together?
Yes.
Okay.
Yes.
Measure that. Kuna gazi hapa mtu ajui test yake. Oxygen, hydrogen, carbon 4, ammonia, chlorine, HCl, hydrogen sulfide, sulfur 4, nitrogen 1 oxide. So, measure that we are able to know. Yeah. That one you can summarize. Indio? Yeah, look at that. Also look at the uses of the gas. Very important. Now, we go to examination content. We now go to the question on analyzing flowchart. These ones are very common in your paper 2 exams. However, we are going to give you a question on the Ostward, the Solvay, the frac process bayers, large-scale manufacture of HCl, fractionalization of air, extraction of metals. Hizi hamjafika huku, hatujafika mambo ya extraction of metal. This one, we are yet to tackle that. Electrolysis of sodium, aluminum, things like that. This is what will be tested. What are the raw materials and what are the sources of the raw materials? So this one is very much important. Chemical reaction is about the chemical properties that are involved. That's very much important for you to be able to understand. Very important. Tukosawa, you have taken a screenshot of that? Huh? Because I want to go to this is what is tested. So when you're preparing, you can write Ostward. You give what are the raw material for Ostward, what are the raw material for Solvay. You write it. You go to what are the impurities that are removed and why are they removed? What are the chemical properties under Solvay? All those kind of things. You go to pollution effects. Under this one, you're going to find the things like nitrogen 2 oxide, sulfur 4 oxide, even nitrogen. All those ones, they bring about acid rain. We have carbon 2 oxide, brings about global warming, not greenhouse effect. Greenhouse effect does not give you a mark. Very important. Then effect of the plant on the environment, recycling. What do we need to recycle, by the way? In all the reactions, in all the chemical product you're going to deal with, what is the importance of recycling? There are only two reasons why we recycle. In any chemical process, there's only two reasons why we recycle. Why? Why do we recycle?
Reduce expenses.
Reduce what? To minimize running cost. That is how to reduce the expense. That is simply to minimize running cost. Number two, Joshua Kalenga.
To minimize environment pollution.
So the only two reasons: minimize running cost, rather to minimize running cost, and also to minimize pollution. Those are the two main reasons. So let's now analyze the flow chart, the industrial process that you have done in case of Mesao. Let's start with factor 4. Okay, what is this now? Just give me 1 minute. Okay, there's something I want to do. Okay. You're seeing the shared screen?
No.
You're not seeing it. Sorry.
Not yet.
Okay, I just saw it.
So, come on. Jesus Christ.
You're seeing it?
Yeah.
Yes.
Yes.
Yes. Yeah.
So that's now
Yes.
for the industrial manufacture of sodium carbonate. So this again is an Octopus flowchart that is drawn right from the UPA command center, and that captures all what can be tested, and of course the things that are normally tested. So let's go through it. We have the raw materials. The raw materials in the manufacture of sodium carbonate. We have the brine. We have limestone. We have coke, and we have ammonia. Sawa? Now
Yes.
from there, I want us to be very clear. I want to take you through this kind of question, whereby now we are going to have we have brine here, sorry. We have brine. So brine is a liquid that is concentrated sodium chloride. Henry Kazush, uliza. Henry, is somebody else? Henry,
Sorry.
Yes.
It was
You think? Henry.
it was a mistake. Sorry.
Okay, so.
It was a mistake. I'm sorry.
I've understood. I've had no problem. There's no problem about that. So we have industrial manufacture of that. So let's look at. So we are looking at that, and we want to see the industrial manufacture of so in that kind of a scenario, we have the raw material and we have the ammonia absorber. The first reaction occurs in the ammonia absorber, whereby we mix ammonia and brine. So what happens there? What happens? What happens in the ammonia absorber? Mwenda, Dave.
The brine is mixed with the ammonia to form ammoniated brine.
Ammonia is simply mixed with brine to form ammonical brine. Ammonical brine is simply a mixture of ammonia and brine. Simply that is it. Normally, remember, we are putting the liquid, we try to play the liquid from the top. Then we allow it we have the chamber. So the liquids are supplied from top while the gases are supplied from the bottom. So that as the gases rises and the liquid is trickling down, it ensures proper mixing of the what? Of the gases with the liquid. So we cannot put the gas from top and the liquid at the bottom. They will not mix. Are you get the point?
Mm-hmm.
Yes. So so you put the liquid from here and there is the gas here. So the gas, remember this ammonia being lighter than air will try to rise up. So it rises up, it will mix with the gases. So it ensures proper mixing of the two components, that the liquid from the top and the gas from the below. So now what we have here, we have the ammonical brine. The ammonical brine is taken to the, and of course, before I continue, remember in this chamber, we may also have something like this. These ones are called the buffers. These are called the buffers. So what the role of the buffers? That will be put in the ammonia absorber and also in the ammonia generator. What the role of the buffers? Make Melky Obongo. Steve,
excuse me, sir. What does?
What does?
Brine consist of?
Brine is simply concentrated sodium chloride. That is what is called brine. Gosawa?
Yes.
Joshua Kalenga? Joshua? Okay, Jeff? Unmute yourself.
Yes. The baffles are used to allow the liquid to trickle down slowly to allow more time for proper mixing of the gases.
Yeah, so the buffers allow the liquid to trickle down. You know, this is like, for example, when you have something like this, the buffers or something like that are put in the, like if you have this glass and you are putting some like figures like this, if you are putting a liquid, it slows down the flow of that particular liquid. And that kind of a scenario, it allows the liquid to trickle down slowly to allow for more time for the liquids to mix with the gases. Are we together? Are we together? Perfect. So now, then we have the ammonical brine. Remember, ammonical brine is a mixture. We have ammonia and we have sodium chloride here. So we need to know what takes place in the Solvay tower. So in the Solvay tower, there are two reactions that takes place there. We have brought ammonia we have also brought sodium chloride. So in that kind of a, remember we are here. So we already have brine, which is sodium chloride, and we have ammonia. That is now the ammonical brine is taken to the Solvay tower. When they are taken there, in the limestone kiln, we have coke that we are seeing here and calcium carbonate. So these two are used to generate carbon dioxide this way. So in the kiln, we have calcium carbonate decomposing in the presence of it to form calcium oxide and carbon dioxide. We can also have coke being burnt in presence of oxygen to form carbon dioxide. So in the kiln, we are generating carbon dioxide, which is now taken to the ammonia generator and should be supplied from the bottom, so that the ammonical brine is now supplied from the top. Are we together?
Yeah.
Yes.
And now,
Yes.
I think maybe somebody is wondering, now we have ammonia, we have brine, we have carbon dioxide. Somebody might be wondering, and where is this water coming from? And we are not seeing it here. Is there somebody who is asking that kind of a question?
Pardon?
I'm saying the reaction that is taking place here, we have brine, that's sodium chloride, we have ammonia, and we have carbon dioxide. But we also have water. Could there be somebody who is, where are we getting water from? And we don't see anybody bringing water here. Yes, Jeff.
So some water can be recycled from the reaction that takes place in the roaster, where these,
Before you recycle, you must have the water. So where is the water?
Yeah.
Floridos.
Somebody?
Some water.
Yeah? Who is that? That is Steve Otieno, yes.
Can we say because the process takes place near a river or a water source?
Not really. Okay. Kuna mwingine nimeona amenyanyua mkono. Who is that? Okay, can I give you the answer?
Yes.
Yes. Yeah, remember you are saying, look here, we are talking about sodium chloride aqueous. Even you talk about brine, is made up is a solution, concentrated solution. A solution will always have water. Are you get the point?
Yes.
The solution already has water. That's why you may find here you're not seeing the water being added there. But of course, these things are also located near a river. But already remember the solution already has water. So when you are told to write, unless somebody has told you to write two reactions, ukiambiwa tu uandike equation, just pick the reagents. We have sodium chloride, we have ammonia, we have water, we have carbon dioxide. The product are ammonium chloride and sodium hydrogen carbonate, period. There is no balancing. The equation is already balanced. So if the examiner just tells you to write the equation, that occurs in the Solvay tower. Remember the reagent. We have sodium chloride, we have ammonia, we have carbon dioxide, and we have water. Those four, when they react, they give you ammonium chloride plus sodium hydrogen carbonate, like that. And then when they are formed, before we go to the what happens after that, remember somebody can tell you to write two reactions that occurs in the Solvay tower. So tunakuanga na the equation that occurs in the upper part. The upper part of the Solvay tower, we have ammonia, we have water, we have carbon dioxide and water. So whatever happens there is the upper part, we are having the gases because they are light, they occur in the upper part. So we're having now ammonia plus carbon dioxide, plus water, you get ammonium hydrogen carbonate. The ammonium hydrogen carbonate react with the brine, that is sodium chloride, to form where we just have the exchange. We have ammonium chloride plus sodium hydrogen carbonate. When these ones are formed, ammonium chloride is very soluble, while sodium hydrogen carbonate is less soluble at that low temperature. So at that temperature, sodium hydrogen carbonate is formed as a what? It is formed as a solid. And ammonium chloride is a what? As a solution. So you have a solid and you have a liquid. What do? You filter. So that's why you're saying from here we go to the filtrate, whereby you're going to have, we go to the filter, whereby you're going to have ammonium chloride being a filtrate and sodium hydrocarbonate as a residue. So once this one is formed, remember this process is to manufacture sodium what? Is to manufacture sodium carbonate, not sodium hydrocarbonate. So the sodium hydrocarbonate is taken to the roaster, whereby now it is heated to produce sodium carbonate, carbon dioxide, and water. The carbon dioxide and water, because they are reacted in the Solvay tower, they are recycled back. Are we together?
Yes.
Perfect. Good. Now, from there, at the limestone kiln, we are going to have calcium oxide here, which now is taken the slacker. Slacker is simply adding water to a compound. So you add water to the calcium oxide, you get calcium hydroxide, as you can be able to see here. The calcium hydroxide is taken to the ammonia generator, whereby it will meet with the ammonium chloride from the filter. And these two now, when they react, ammonium chloride plus calcium hydroxide, if you can remember, that is the equation whereby we used in manufacture of ammonia. Munakumbuka?
Yes.
Exactly. That is where now you're even going to understand it better, because even you're from two, but now at least you have already prepared ammonia. So this is the reaction that we use to manufacture ammonia. So when you have the ammonium chloride from the filter and calcium oxide, which now comes from the kiln, it is mixed with water to form calcium hydroxide. Now this one, they form calcium chloride plus ammonia plus water. The ammonia formed here is regenerated back. It is regenerated back to where? Because remember here remember this is the ammonia, main source of ammonia. Then this is the ammonia, which is now recycled. So it is taken back to the ammonia absorber, whereby the reaction proceeds again. So this is the reaction is the ammonia generator. And then now, this is the reaction in the slacker, whereby we have a calcium oxide plus water is equal to calcium hydroxide. Any question? Is that clear now?
Yes.
Na mjue pia mtihani italetwa hizo vitu zikiwa zimechora vizuri hivi. Wewe angalia mahali kama umeona mahali kunatoka carbon dioxide, that might be the limestone kiln. Umeona mahali kumetoka ammonium brine. Ammonium brine inapelekanga kwa ammonia generator, that it is taken to the Solvay tower. So from there, just follow the chart to know where is the questions being directed to. It becomes very easy. Somebody will tell you this is the main byproduct here, the calcium chloride, which can be used as a drying agent for gas in the laboratory, and also is used in extraction of sodium. It is used in extraction of sodium as an impurity. Very important. Now, we continue, and somebody will also ask you why this Solvay process is considered a very economical process. Why is it considered a very economical process? Somebody else apart from Jeff, want to pay Gina? Hey, this number one chemistry fund, mwenye ana Gina, atupe.
This is because most of the products such as water and carbon dioxide and ammonia are recycled.
Yeah, this is because most of the byproducts, that's ammonia and carbon dioxide, are recycled. We already gave the role of the recycling. So, and why is it that we cannot prepare potassium carbonate using this method? Why is that we cannot prepare potassium carbonate? Gabriel, Mwangi.
Will you say because potassium carbonate is highly soluble in water, thus it will require high amount in order to extract it?
Yeah, that's correct. That the solubility of ammonium chloride and potassium hydrocarbonate is the same, and therefore it will be difficult to separate the two. So sodium bicarbonate is less soluble, while ammonium chloride is very soluble. So we are able to separate it using either filtration or using fractional crystallization. But now with the potassium hydrogen carbonate, it has almost the same solubility as ammonium chloride, and therefore it will be very difficult to separate the two. All right. Ashika?
Yes, sir.
Yes.
Valentine Ongwaya, sijui ni Ongwaya ama uliza?
Sorry, it was a mistake.
Okay, good. Perfect. Now, why should this this process be located near a river? Yes, there are some guys who have raised their hand. I don't know them. So I'm not able to see. Okay, I can see. Jeff, Steve, Otieno, Gabriel. I'm Steve. Steve Diujaji.
Because the reaction in the Solvay tower is exothermic, so there need to be cooling.
Yeah, because the reaction in the Solvay tower is exothermic, so the cooling is needed. Water is needed as a reagent, and water is needed as a coolant. As simple as that. Next. We can go to another one. This one, I don't think there's any. Have you taken a screenshot on that?
Yes.
Yes.
Do you have anything about, I think ammonia is so direct. Anything that you need here? Ama tupitie tu. Yes. Yeah, I can take you through that. So now, in a Haber process, that is manufacture of ammonia, I'm looking at hydrogen. The reagents will require nitrogen and hydrogen. The examiner will ask you what are the sources of hydrogen. You have the cracking of hydrocarbons, rather. We also remove arsenic oxide. So the dust particles, arsenic oxide, carbon dioxide is removed in the purifier. So why do we need to purify the gas? Why do we need to purify the gases?
To prevent them from contaminating the catalyst.
Coño. Alex Marogori, estimate, can you make the cost? I'm not getting anything. Who is that? Diesel. Diesel, angalia your network. Iko na shida. So you mean, guys, are you there?
Yes.
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 Students, are you getting me or I'm alone?
I'm getting you.
We're getting you.
Getting.
Hello? Are you hearing me? I'm asking the role of the purifier.
Yes.
Why do we need to purify the gases? That's a very simple question. Gabriel.
To prevent the impurities from poisoning the catalyst.
The impurities what? I think I lost you. Gabriel?
I say to prevent the impurities.
Is it my internet or
to prevent the
Gabriel. I don't know. Ama, it's me. Jeff, what does he say?
To remove any impurities that may poison the catalyst.
Jeff, can you answer the question?
To remove any impurities that may poison the catalyst.
Yeah, to prevent poisoning the catalyst. Impurities poison the catalyst. That's the reason why we need to remove them, rather to avoid poisoning the catalyst. So we go to the compressor. Remember, first of all, we said we require the raw materials. The raw materials, nitrogen and hydrogen. We have looked at their sources. Conditions, we require iron catalyst impregnated with aluminum oxide as a promoter. So the iron catalyst is finely divided to increase the surface area. Then we require a temperature of 450 degrees Celsius and a pressure of 200 to 500 atmosphere pressure. So that's why we are compressing it to attain the required pressure for reaction to occur. Then from there you go to the heat exchanger. What are the roles of the heat exchanger, by the way? What are the roles of the heat exchanger?
Heating the gases.
Steve, what you know?
To preheat
Maintain temperature for the reactions.
hydrogen mixture.
What are the roles of the heat exchanger?
To preheat the nitrogen and hydrogen mixture.
Yeah?
And also to preheat the nitrogen and hydrogen mixture, and also to cool the gases from the heat exchanger.
The role of the heat exchanger is to heat the incoming gases, that is now the nitrogen and hydrogen, and also to cool the ammonia produced. Simply, the role of the heat exchanger is to maintain the reaction temperature. That's it, or rather to recycle it. So it is to heat the incoming gas, that is now the nitrogen and hydrogen, and also to cool the ammonia produced. Are we together?
Yes.
Yes. Are we together?
Yes.
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 Yeah.
Yes.
Yes, we are together.
Are you getting me, student?
Yes, we are.
Yes.
Yeah?
Yes.
Yes.
Yeah. Yes.
Yeah, I don't know what the problem is, you people. Are you all in a place where there is no network?
No.
So somebody is asking how the compression of gas is done. So during compression, the gases are taken in a chamber whereby their volume is drastically reduced. You know, just like, for example, if you want to increase the pressure, you reduce the volume. So you reduce the volume of the gases, and by that now the pressure increases. Of course, we have the machine that do the compression. So remember, once you go to the heat exchanger, the gas are taken to the catalytic chamber, whereby we have the catalyst. So the reaction occurs, forming now, this is the reaction that occurs in the catalytic chamber to form ammonia. Then now we have this one should be showing you, I don't know. This one should be showing you the reaction that takes place. And let me see. Be something like this for reversible reaction. They should be looking like that. So we have those kind of scenarios, that's the equation that takes place there. Once the ammonia is produced, it is taken back to the heat exchanger for cooling. The ammonia is cooled. Then now the ammonia, after once it's cooled, is taken to the condenser, whereby you get the liquid ammonia. Then the nitrogen and hydrogen, after condensing, the ones that are not reacted, they are taken to the recycling pump and taken back to the compressor. Now, what are some of the uses of ammonia? What are some of the uses of ammonia? Jeff?
Ammonia is used in softening hard water.
Ammonia, you have got lost again. Victor,
It
Gabriel.
is used in softening hard water.
Are you getting me? All my network has issues.
Yes, we can hear you.
Can hear you loud and clear.
Your network.
We are getting you, but
Okay,
it
let me
seems
change.
it's a bit slow from your side.
Let me change.
So as Mwalimu is doing a network change, well, let's do an roll call very quickly. Just look at your screen and take a roll call from your class.
Mr. Obero, are you getting me? Okay, record.
Yes, sir. I can hear you. I can hear you, sir. Okay. I can hear you very well. I can hear you. So boys, let's take the roll call in the quickest time possible. Can see from A, B, only 20 students have answered from A. 71% of you have just answered. It should take you less than 2 seconds to finish. Okay, 77%. What I just need is just 80% as well. And this data is shared with your parents later to confirm those who are in class. At 79%, we still have around 46 students have not answered.
Excuse me.
Yes.
Yes.
I cannot see the where I can take the roll call.
Maybe so. You just write a message at the chat. I can check that. I'd rather have that manually added. So we're at 85%. That is better. This is better now. 86%. The others will take longer to respond. Should at 86%, we can end there. 87. Okay. I think we now stop the roll call. Right time. Mwalimu, you can proceed.
So I continue. Okay, are you able to see my screen?
Yes, sir.
Okay. Now, I think now you are getting me clear.
Yes.
Okay, perfect. That's what I think.
Yes.
I think the network was issue, so I had to change. So now I think now that's okay. Now we go to the next, and you see now, as you're going to see, now look at this. Now this one manufactured 85 acid. This one now, yes.
Why do you produce the ammonia in liquid state and not in gaseous?
Why?
Why do you produce the ammonia in liquid state and not in gaseous state?
Why do we produce ammonia in liquid state instead of gaseous state? That's what you're asking? Yeah, because of storage. Assume now, to store a gas, like for example, just even go to the lab in Alliance High School and tell Pauline to give you 2 liters of carbon dioxide or 1 liter of chlorine. So you see now, it is easier to store a liquid and a solid than a gas. So that is now for easier storage and transportation. And that's a very magnetic question, by the way. Are you get the point?
Yeah.
It is easier to transport something that is a liquid and that is a gas. And of course, it's almost stable in liquid state than we have some guys there who are not normal. Now we have Ostward process. What are the conditions? The raw materials are there. I don't think we need to explain anything that is there. We have the raw material, we have air, ammonia, and water. Conditions require platinum catalyst that is mixed with rhodium as a promoter. So the catalyst that is used in Ostward, or rather manufacture of nitric 5 acid, is platinum, not rhodium. Of course, in the book they have said platinum, rhodium. That's correct. That means the rhodium is a promoter, just like we use aluminum oxide in the manufacture of ammonia as a promoter. So, but the platinum is a catalyst. So, you can take a platinum with a score, platinum rhodium with a score, rhodium wrong. They require 9 atmospheres and a temperature of between 700 to 900 degrees Celsius. Mwendo Anthony, you can ask a question.
Kindly pardon the catalyst in the preparation of ammonia or the manufacture of ammonia.
Ammonia, the catalyst is iron.
Just
It
iron.
is iron, yes, just iron.
Okay.
Yeah, so you hear about finely divided iron, that is simply describing why it's finally dividing it is simply to create more surface area for the reaction. But the concept is simply catalyst is iron. It is mixed with aluminum oxide, which helps to improve the efficiency of the catalyst. So now again, when you have ammonia, we are getting ammonia from the Haber process, then we have air. The gases are normally purified and compressed. When they are purified and compressed now, we take them to the heat exchanger, and from the heat exchanger, go to the catalytic chamber. The catalytic chamber, these are the main reactions. The first reaction occurs in the catalytic chamber, and you can be able to see it. This is it. So now we have the catalytic oxidation of ammonia. The ammonia reacts with oxygen to form nitrogen 2 oxide and water. If you don't know how to balance this one, I've already told students who will be talking about 45, 46. That's the way of balancing the equation for this. But of course, I know you know how to balance that equation. So that's the first equation. And many students, they get confused and they think we are getting nitrogen 4 oxide here. We are getting nitrogen 2 oxide in the catalytic chamber. So now when it is formed now, the hot nitrogen 2 oxide taken to the heat exchanger for cooling. Once it has been cooled a little bit, remember, you cannot produce nitrogen 4 oxide when the temperatures are very high. So the reaction here occurs at the temperature of about 700 degrees Celsius. That's a temperature that can melt a very senior ghost. Maybe those are the temperatures that you're going to experience in hell. For those who will be unlikely to go there. Those are very high temperatures. With that kind of a scenario, nitrogen 4 oxide cannot be formed at a temperature of about 800 degrees Celsius. So therefore, once it's formed, taken back to the heat exchanger for cooling, then now taken to the oxidation chamber, whereby we're going to have the nitrogen 2 oxide reacting with more oxygen to get nitrogen 4 oxide. Are we together?
Yes.
Yes.
So now, once
Yes.
the nitrogen 4 oxide is formed, it is now dissolved in water to form nitric 5 acid. Of course, there are these two reactions that take place there, but just focus on the final reaction. We're going to have the nitrogen 4 oxide reacting, being dissolved in water in presence of oxygen to form nitric 5 acid. And those are the main reactions that occur there. Then you're going to be told what are the pollution effects that occur here. The pollution effect that is associated with the manufacture of nitric 5 acid is the release of nitrogen 2 oxide and nitrogen 4 oxide to the atmosphere. Remember, when you're explaining the pollution effect and you want to explain it using the nitrogen 2 oxide, remember you have to say the nitrogen 2 oxide is first oxidized to nitrogen 4 oxide, which dissolves in rainwater, forming acid rain. Then we also have nitrogen 4 oxide, which now dissolves in rainwater, forming now acid rain. That's very much important for you to be able to understand. Yes, question? Any question? Any question? Okay, someone to mute those guys. Sammy Nelson, you have a question you can ask?
Why is it in the manufacture of ammonia and nitric 5 acid, when the gases are going through the heat exchanger, the lines are not straight? They're always curved or wavy.
Oh, the lines. I think that the drawing of that. Of course, I think because of I think that one I need to get a better question for that. A better answer for that. I think by for that. Huyu alitolewa na sijui kwa nini hapo huko. Brian Rafa. Do you know that student? Bramwell Rafa. Do you know him?
No.
Okay, so we reject. Now, so for that one, I may not, let me check if I'll be able to get a better answer, more refined answer on why the lines are not straight on that kind of a thing. For now, I'll be able to give you a better answer for that. Now, we continue and we go to the pollution effect. We have talked about it. The use of nitric 5 acid. We have the use of nitric 5 acid is used in what? Manufacture of? Can somebody give Collins, Kibadi?
I wanted to give a suggestion as to why those lines are wavy.
Yes.
If we could see from the catalytic chamber, there is hot nitrogen oxide and air, whereas after the heat exchanger, there is cool nitrogen oxide and air. So the wavy lines are a representation of an increase in surface area to lose heat. In order for the hot nitrogen oxide and air to become cool.
So the wavy line is representing what?
The increase in surface area of the passage of air.
Yeah, the increased surface area that allows the cooling effect. And that anybody with another question, another answer like that, I think that is I still go with that, of course, but we'll also be able to see if there's any other reason why when you're drawing them, like they should be drawn in a wavy, like I think that's more physics than chemistry. So Colin will talk about the concept of the increased surface area that allows the cooling effect of that, and that's a very, very good suggestion. Now, when you go to use this, I'm waiting for a user. This one is used to manufacture what? Nitric 5 acid. I'm waiting for answers for that. I think that's a very simple question. The uses of nitric 5 acid, because I don't want you to make mistakes. So manufacture of fertilizer. You know, there's a reason why I'm asking this question, because you'll be given those questions and you're going to get zeros. So first of all, there's somebody are saying, many of you are saying used to manufacture fertilizers, and those are wrong answers. Nitric 5 acid is used in manufacture of nitrogen fertilizer, or you give the specific answer, is used in manufacture of ammonium nitrate. Are we together?
Yes.
Ammonia and nitric, yes. When you're told to give the use, say it is used in manufacture of ammonium nitrate, or it is used in manufacture of nitrogenous fertilizer. That's the most correct answer. It's used in manufacture of explosives like the TNT. And what the meaning of TNT?
Nitrotoluene.
It is
nitrotoluene.
And by the way, I forgot to give you when I was dealing with the preparation of gases that I'll come back to that. Make sure that you're able, anytime you see any abbreviations, be able to know their meaning. I know there's many people who could not understand the meaning of a TNT, the meaning of CFC, the meaning of DDT. So those are things that as you learn, make sure that you're able to understand those kind of things. And I think now with the nitric 5 acid, we are done. Can you take a screenshot, or rather you have already done it?
Yes.
Good. We go to the next.
Is the platinum in both the oxidation chamber and the catalytic chamber?
Yeah, is there?
The platinum catalyst, is it in both of them? Does it help in both of them for reaction in the oxidation and catalytic?
No, the catalytic chamber we only have the what? That's why we have the platinum, only the catalytic chamber, not in the oxidation chamber. Remember, the role of the catalyst is to oxidize, to catalyze the oxidation of ammonia to nitrogen oxide. That's the most important thing. And the catalyst is only used in the catalytic chamber, not in the oxidation chamber. Sawa?
Yes, thank you.
Okay. Good. Then we have the conduct process for the conduct process. My cookie is up. Don't know whether I could do the biscuit. So we have the one for conduct process. We have the raw material. We have air, water, metal sulfide, rather sulfur. Then we have conditions is the 105 oxide. We have platinum. We have 2 to 3 atmospheres. Then we have 500 degrees Celsius. So now once we have this one, now again we also have the air, then we have the metal sulfide. So we have the first roster. The roster, we are going to have burning sulfur. The role of the roster is to produce sulfur oxide, which is produced in 2 ways. You can burn sulfur in here to get sulfur oxide, or you can burn we can have the metal sulfide being burned to form the corresponding metal oxide plus sulfur oxide. Right? Are you got that?
Yes.
Then now the purifier, the gases are purified to remove impurity that may pose on the catalyst, then dried, then taken to the heat exchanger. So the heat exchanger to heat the gases to the required temperature. Then from there, once the gases are heated, we go to the catalytic chamber. The reaction that occurs in the catalytic chamber is this one. The sulfur oxide reacts with oxygen to form sulfur 6 oxide. And of course, as I said, this one represents the reversible reaction. Remember, this one is a reversible reaction. So that's why we have this kind of a scenario, that's the equation that occurred there. Then from there, we go to the absorption tower, whereby we are now going to have the sulfur oxide. We go to have the sulfur oxide. Now it is formed there, it is cooled. Then take up the absorption tower, whereby we are going to have the sulfur oxide being dissolved in sulfuric acid to form oleum. There's no balancing here. Unachukua hii, unaileta hapa, then you form the oleum. Oleum is just a very concentrated sulfuric acid. What does it have? Iko na hydrogen, iko na sulfur, na iko na oxygen. This is how you get the formula. Unakuja kwa hydrogen, ni ngapi zenye ziko hapa? 2. Unakuja kwa sulfur, kuna moja hapa, kuna moja hapa, 2. Oxygen, how many are they? 3 from sulfur 6. In from sulfuric acid, they become 4. They become 7. That's whereby you get helium. So it's very simple as that. So even if you get confused, you forget how to write the formula of helium, you can simply look, you can simply get it from the reagents. Helium iko na hydrogen 2 zenye zimetoka hapa. Sulfur ni 2. 1 here, the other one there. Oxygen ni 7. From where? 3 and 4. Just like that. Then from there, after forming, and of course, there's a question here. Why sulfur 6 oxide is not directly dissolved in water to form sulfuric acid, and instead it's first of all dissolved in conc sulfuric acid? Why is that we don't dissolve it? We don't dissolve sulfur 6 in water. Why? Steve, not you, America.
The reaction is highly exothermic, so the solution formed will boil, forming a mist of tiny droplets.
So the reaction between sulfur 6 oxide and water is highly exothermic, and it forms harmful acid droplets. That's it. They react with the acid exothermically, releasing harmful acid droplets. Very important for you to be able to understand. Then once you get the helium is and I want you to capture that word. The helium is carefully diluted with water to form conc sulfuric acid. The helium is carefully diluted with water to form conc sulfuric acid. Very important for you to be able to understand. So again, you can be told to give the precaution that is done here, that the oleum is carefully diluted with water, or rather controlled amount of water. You don't just add any water. You add a controlled or rather fixed amount of water to avoid now producing a very dilute acid, because here you should get 98% sulfuric acid. So there's the element of carefully diluted with water. Then we have now the unreacted sulfur 4 oxide. The unreacted sulfur 4 oxide now, after from the dilution chamber, it is now taken to the recycling, and also the main pollutant in conduct process is sulfur 4 oxide, which can be removed using scrubbing. So we have the reaction, the scrubber, whereby the sulfur 4 oxide is passed through long chimneys lined with calcium hydroxide, whereby now it reacts to form calcium sulfide plus water. Somebody can tell you to write the equation for the scrubber. Is very much important for you to be able to understand. You can also be told, apart from scrubbing, which are the other methods of reducing pollution? Which is the other method of reducing pollution? Yes, Collins.
Flue gas desulfurization.
Yeah, the flue gas desulfurization device, the FGD, and also recycling. That's also recycling. That's very much important for you to be able to understand. Yeah, before I forget, I want to remind you that this is something that we had set in a test for gases, that you can also collect a gas like nitrogen using mercury. So like the one that we have given you, that was liquid mercury. Instead of water, you can put liquid mercury here. If you want to collect oxygen, dry oxygen, you can now collect it using what you call the liquid mercury. So like the question that was brought in your exam. There's also something that I want to give. I want to under industrial processes. Let me see if it is here. Okay. Are you seeing my, okay, you're seeing my shared, sorry. Are you seeing it?
Yes.
Yeah, so this one now, the process for the extraction of sulfur. And of course, I think everything is just direct that now. In the outermost pipe, we have put superheated water at 170 degrees Celsius and 10 atmospheres. 10 atmospheres. The role of this is to melt the sulfur. So this diagram, remember, these are flowcharts that are drawn because of by the fact that now sulfur is yellow, water is blue. That's why we are giving it the color blue. And then this is the sulfur deposit, which is yellow. That's why the role of this one is to melt the sulfur. And sorry. The role of the superheated water. And somebody will ask you, how is water maintained in liquid state above its boiling point? Remember, water boils at 100. How we talk about the water at 170? How? Yes, Sami?
The water is kept under high pressure.
Yeah, the high pressure. Remember, high pressure increases the what? The boiling point. Then the middle pipe, the innermost pipe, we are putting hot compressed air at 15 atmospheres. The work of this one is to force the molten sulfur out through the middle pipe. This is whereby we are pouring the molten sulfur and water. Remember, sulfur and water, they don't mix, of course. So they are normally, when they are mixed, they are simply separated because molten sulfur is a little bit molten sulfur is immiscible with water. So it's going to form two layers, and of course, will be collected separately. So the impurity that we can find in this sulfur include, we have soil, we have sand and silica, because we're extracting these things from the ground. So that's why it's going to contain silica, clay, soil, and sand. What are the physical properties that make this extraction possible? It's captured there. We have the low melting point of sulfur. Sulfur is insoluble in water. And of course, these are the same method. The first 2 points are enough. Low melting point of sulfur and sulfur is insoluble, rather does not react with water. Or sulfur is immiscible with water. All these points, they mean the same. Sulfur does not react with water. Sulfur is immiscible with water. Sulfur is insoluble in point. So when you're told this method is suitable, is because sulfur has a low melting point, and also it is insoluble in water. The thing now being 1322, I think we can come to the end of this lesson. If you have a question you can answer, make sure that you're also having this flowchart is called the Octopus technique, and you can be able to see they are found in that small book, the biology and chemistry Octopus flowchart. So you can still be able to get it from there. You can continue utilizing it. I want to believe that you have had a very, very magnetic session. I've seen you go up to around 257. We have come to the end of the lesson. So maybe I wish you the best. Have a very, very magnetic day. If you have a question, some other question you can ask. Or you can write in the chat. Even the presentation is very much important to be able to understand. Have a good day. The lesson is over if nobody has a question.